Okay. So, let me just repeat what I said few minutes ago. In the last class we talked about the heterocycles and the radical reactions, right. And the radical reactions is pretty famous now in organic chemistry because of many reasons. One of the reasons why radicals are popular, because they can survive in water solutions, and number 2, it does not promote, the radical reactions do not promote any elimination reactions. We will have plenty of examples today. Okay. And then what else? Third thing, that it can be done in acidic conditions, basic conditions, that means they are not affected by the changes in pH, and then also they are not very susceptible to these other reaction conditions. Then radicals are generated normally by again two different kinds of general methods. One is the oxidative reagents, oxidizing agents, or the reducing agents, like including lithium, liquid ammonia, they are all reducing agents, tertiary butyl tin hydride, then indium chloride, sodium borohydride, all these, they are all basically the combinations of the reducing agents, except of course hydrogen. Hydrogen does not produce any radical reaction. Then oxidizing agent could be manganese triacetate, lead tetraacetate, phenyl iodinium acetate, and steric ammonium nitrate, all these are the oxidizing agents. Then we had looked at extensively these Minsky reactions. Minsky reaction is going to be very popular very recently, and you have not got hold of the review, but I could recently one person has reviewed the reactions, Minsky reactions used in medicinal chemistry. So, you can think about it, that means it is primarily useful for medicinal chemistry. And if you recall, in the last class we talked about extensively of the radical carbon radicals towards the pyridine moiety, pyridine derivatives. Also as an illustrative example, we also showed something else, that a complex molecule like quinine can be functionalized at a particular position. Of all possible positions, only one particular position can be functionalized, that is 2 positions of the quinolide moiety, right. Also we have noted one more important thing which is otherwise impossible, that if you start with ethyl pyruvate, it can provide a functional group which is not normally directly accessible, that is ester group. I mean if you can think of alternative, you will not find an alternative that by which one can just directly deliver a carboxyl ester group to a nucleus. Okay. So, that means some of the reactions in radical chemistry are very remarkable. Okay. And today, as I said before, again we will just see a duality of the reaction pattern in the Minsky reactions. Then also we will talk about these functionalization of the 5-membered heterocycles. How to do 5-membered heterocycles? There are not many options actually available. Although Minsky is applicable to 5-membered ring, but you have to have at least 1 or 2 nitrogens in it. And but normally we will see that under certain cases 5-membered also can be functionalized, provided there is a limitation, or there is or I should say there is a guideline under which condition 5-membered ring can be functionalized. Just the reverse, if you in Minsky pyridine is the electrophile. So, the carbon radical is almost always nucleophilic, almost not necessarily, but compared to pyridine, yes, carbon nucleophiles are nucleophilic. Just change the situation, change the situation. So, pi excessive heterocycle means 5 members are nucleophilic. So, if you have electrophilic kind of radical, then obviously functionalization should take place. Okay, we have a few examples. Then we will go on and see and how to construct the heterocyclic ring systems. Okay. I mean these days it is a very popular way of doing it, but that exclusively are used for non-aromatic heterocycles. Understand what I am saying? It could be normally, but we will look at some of the examples that will give you some of the ideas, and some there are in fact radical chemistry can solve many unsolved problems. Okay. Let us look at this special Minsky reaction. Here is a case, again the same old quinolene and 4 position is blocked. So, that you do not get now without looking at if you can see write the product, this is the carbon source and the reagent is ferrous sulphate and ammonium per-disulphate, Okay. So, what would be expected? Just by looking at, you can see that ammonium per-disulphate is there. So, it is a peroxy compound. So, it is likely that the radical would be generated from there, peroxy. So, sulphate anion radical that would create another carbon radical. Now, in this case I can give you the answer. The answer is this. What it means? This is equivalent to a radical of this kind. So, again it is basically a manifestation, this is a redox potential as well as manifestation of the tertiary amino group effect. That means, this lone pair of nitrogen stabilize the radical, and see the combination. On previous occasions we had only ammonium per-disulphate, not in the ferrous sulphate. Ferrous sulphate is normally is used in the DMF, and then ferrous sulphate normally is used in combination with a hydrogen peroxide or the corresponding substitute, that is soluble substitute, that is tertiary butyl hydroperoxide. Under these conditions, so what do you expect? As I said, there is a duality in the reaction mode, and what you will find the again there is another possibility that it can simply deliver the amide group. That means, the radical that was generated is acyl radical, this acyl radical. So, I mean, is there any prediction? No, absolutely no. At least one thing one can be done, that the conditions can be modified to see whether that can be done, this can be done, that is another thing. And let us say next item is the functionalization of the 5-membered heterocycle. One can think about let us say this is pretty I think this is a reaction quite popular also in chemistry. Suppose you have an oxygen up here, oxygen is, and this is diphenyl ether. Then if you have a diazonium salt and treat these with copper 0 or copper 1 like cuprous iodide, you can expect what is the reaction. Normally, the reaction that is expected out of the diazonium salt and the copper salt is the basically dimerization, Ullmann coupling. But also we know that if there is a reaction possible intramolecularly, that would be favored than to the intermolecular reaction, and that is what happens. And in this case, what you get the dibenzofuran. So, that means you can and in the place of oxygen one can think of, that means if this is X. So, X could be oxygen, it could be sulfur, it could be SO2, it could be even CH2, it could be even carbonyl. So, such general reactions. So, if it is general reactions, then it should be named, and what is the name? It is known as SOR reaction, ORR reactions. This is a pretty useful reaction. This reaction used to be done in Presidency College long ago when we were student. One D.N. Chatterjee, Professor D.N. Chatterjee used to work on this reaction. Okay. And now, very recently, I think I will give you the reference if you are interested. 2010, I write in brief CEJ, Chemistry European Journal, Chemistry, a European journal, all of us know, and the page number 254. So, what you will do in this article, again a very similar reaction has been done, reported, and what you will find is the substrate is an furan containing amino group, and the other reactant is a diazonium salt, and R often is an alkyl group. Then what? Okay, I'll give you the end product. End product is this amino NH2 also, this. So, what do you find? The yield is good, more than 70 to 80%, but something is missing. What is missing? You have to generate the radical. So, diazonium salt you have to have a radical. Okay. And in previous occasions for reactions, so we have seen copper 0 of copper, but then they are all heterogeneous reaction. So, you have to have a homogeneous reactions. In fact, there is a reagent titanium trichloride. Many of you know this is actually available in water solution. This is water solution. So, if you do so, the reactions actually generates the radical and eventually adds to the now you can guess and the position wise. See, all of us know because of the lone pair effect, the furan is nucleophilic predominantly at the 2 position or 5 position, right. So, 2 position or 5 position. So, and provided furans acts as a nucleophile, and that is what is happening. That means, in this case the radical that is being generated is electrophilic in nature. So, that gives you a nice clear example. What else do you learn from this example? See, basically what we do, we write just reactions, but you have to extract out the useful information from it. What is other striking point about this particular reaction? The amine group is unprotected. So, that means amine is not at all affected by. See, in most other electrophilic reactions, nucleophilic substitution reactions, amines are always protected, but in this case you do not have to worry about the protection. We will see more examples in radical reactions. Similarly, one more reaction, let us say here you have a triester, and then manganese acetate, again an oxidizing agent. Mind it, the previous one was reducing agent, and in this case it is an oxidizing agent, and the reaction would take place fine. So, manganese triacetate is an oxidizing agent. So, it would actually generate the radical like this. So, it is a carbon radical. Now, you have to make a guess whether this carbon radical is electrophilic or nucleophilic. Obviously, because you have 3 ester groups, so they are likely to be the electrophilic in nature, and furans is nucleophilic, and at the same time, so it should work at C2. That means the product would be this one, product would be this one, product would be this one. And then in contrast, if you take a, let us say, pyrrole moiety, and it is a different reagent now, different reagent. What is there? It is a trifluoromethyl iodide, and the other reagent is zinc, and along with that actually we have to question a little bit. In my note it is given Na2S2O5, I do not know what it is. So, I have to check with this. Na2S2O4 is sodium dithionite, right? Sodium dithionite. H2SO5 is chiral acid. That is an oxidizing agent. So, together you cannot use it. So, it has to be an so that is what I am telling you. Maybe there is a mistake, but any case for now, but you just write down that this reaction. I have to check, actually I forgot the source, but as usual the reaction would take place, and halide on reduction gives the corresponding radical. that is almost always starting from the very early reactions called Urge reaction. So, okay. And obviously this is radical, but it is a matter of now which one is whether electrophilic or nucleophilic, and in this case you have again 3 fluorine in the substrate. So, it is likely to be the electrophilic in nature, and you can get directly this sort of a kind of a Friedel-Crafts reaction, kind of a Friedel-Crafts reaction, but in the radical mode. Okay. So, now we go to the next one. The next important topic actually is construction of heterocyclic nucleus, right, heterocyclic nuclei by radical reactions. When I say so, if you recall, I said in most cases the reactions are used for non-aromatic heterocycles. I will give you a quick sequence of reactions that to just exemplify that the radical reactions can be utilized for the construction of the heterocycles. The first few reactions would be for the oxygen heterocycles. This one is I taught you in this 4th year. This is a case of furan construction, and we will just ignore rest of the thing. I think all of us know that if we do a Wittig reactions with methoxymethylidine, methoxy-Wittig reagent, and so the first thing that would take place is the Wittig reactions, there will be formation of the double bond, and I think I will just write this second bracket. Then you do a small manipulation kind of thing. You react with NBS, N-bromosuccinamide, and alcohol, acetylenedic alcohol. I will not tell you the name, some of you know the common name, propargylic alcohol. So, what do you expect out of it? Nothing to do with heterocyclic or radicals, but just a small exercise of organic chemistry. So, what do you suspect? Okay. The backbone remains as it is. How is that? The reaction takes place at the alpha this double bond. So, because of this lone pair actually, then the bromonium ion is captured. That means, you will have a bromine, right, and then this alpha position becomes positively charged, and this portion remains OMe, and then what you will see basically you will get a bromo ether, right, bromo ether. Next is a very useful reaction. Next is a very useful reaction. What you do is a butyl tin chloride you take. Then I will not write something here. You have to tell me, and then one more reagent that is required, AIBN, and then tertiary butanol to solubilize all these things. And then you have to heat it. So, what is the missing reagent? Close, not correct. Na cyanoborohydrate. So, no cyanoborohydrate is basically this combination is equivalent to tertiary butyl tin hydride. So, sodium cyanoborohydrate reduces the corresponding chloride, and this gives AIBN generates the radical. So, that means, and then radical, these tin radicals has obviously it has an affinity towards, all of us by now know it has affinity toward tin as well as halogens, especially bromine and iodine. So, one can then So, one can write that this would generate a radical, and then as usual you have an intramolecular possibility, intramolecular possibility. So, it will undergo intramolecular reaction, and you will have a spirocyclic and as well as spirocyclic heterocycle OMe and double bond, and then you have a radical of here, What next? Then excess tin hydride will be abstracted. So, you will be getting a methylene based compound, So, I mean now the rest of the things are actually in order for the synthesis of the target molecule or whatever, but this is basically what you see here, that this radical can be generated from an halogen compound and the corresponding tin hydride, and that can be added intramolecularly to the triple bond, and the reaction can be stopped there, provided you use excess amount of this. So, then and you don't require any kind of a group on these acid helix center. Acid helix are normally electron unsaturated, right. So, radicals, carbon radicals normally is nucleophilic, that nicely work with this acid helix. Look at another example, is a pretty similar example. Here you have an alkyl side chain, again it is a bromo compound. Now, the oxygen is in a separate place, I have from bromine, and then you have an alpha beta unsaturated system. The reaction condition is slightly different. It is a triethyl boron and butyl tin hydride. When I write butyl tin hydride, actually it means N butyl tin hydride. Then only 0 degree, and the solvent is toluene. So, whenever you see triethyl, actually triethyl boron, it is equivalent to ethyl radical. In the presence of, that you have to remember, in the presence of oxygen. Otherwise, pretty stable. If it is inert, if it is protected from oxygen and water, triethyl boron is perfectly stable, but if you just inject little bit of oxygen, it may catch fire, that pyrophoric. Okay. At the same time, it produces a ethyl radical. This is one of I mean, it is not very popular because it is difficult to handle and sometimes. So, or otherwise, so it produces ethyl radical, and that probably generates the tin radical from there. But then what is the advantage if comparison to the previous example, what is the advantage? You can just guess. Ether is generated, that escapes the solution, that is another point. Important point is this one, temperature 0 degree. You can nicely quickly do it 0 degree. And so, the tin radical then generates the alkyl radical. So, alkyl radical, and now you can say what is the product? Well, the product would be, okay, this is R, I have just reversed it in writing. So, the radical now would be this one. That means, the radical now undergoes Michael kind of addition, right, Michael type of addition. Okay. What next? There are all possibilities. Whenever you have a radical, whenever a carbocation, you have all kinds of possibilities. It can abstract proton, it can eliminate something, it can undergo rearrangement, all these possibilities are there. Okay. But this is where the reaction stops, that is the beauty. What does it tell you? The reactions now stops at this position, and so you will have these groups and these. So, does it tell you anything about anything special? So, you have an hydrogen now abstracted here. So, you get it again in heterocycle, saturated heterocycle. What is the advantage? What is the advantage? Anything special you see, that is what you have to learn. When you read in the literature, when you read a book, See, we keep on giving examples on one after the other, but there are lessons from one to the other. You see something new. Okay, from the first one, you see this is a separate mode of producing a radical from the same kind of substrate, that the bromide, but we see that the temperature can be lowered down to 0 degree because of the okay. And now it is a saturated one. And what else do you see? Okay, normally I will tell you just one very important thing about this organic chemistry. If you try to, let us say, you have something like this, and mechanistically if you have OH minus, what do you expect that these the Michael addition would take place, right? Michael addition would take place, but that is not a very routinely used reaction. Very routinely used reactions. Reason being, I mean, mechanistically possible, thermodynamically probably possible, all these things, but in real life the heteroatom Michael additions are very tough, very tough. And if you are lucky, if you are not expecting, the reaction would take place, something like this. Okay. In most cases unexpectedly take place, but I mean, in fact, at least I cannot define, okay, under these circumstances heteroatom Michael addition would take place, these circumstances it will not. Okay, it is very irregular. Yeah. Okay. So, that is number one. So, that means it is sort of you can say a product that you are getting is just like an intramolecular Michael addition product kind of thing. What else? I have already said to begin with today, when I say the advantages of the radical reactions. If you had a carbon ion off here, you would have expected reverse of this Michael addition, that means elimination would have taken place. Addition, elimination, we have learned plenty of addition elimination reactions. Okay. But this is a kind of a test that the reaction is proceeding through radical reaction, and that is what is happening. And this geometry, the stereochemistry wise, this is also alpha, this is also alpha, that is the outcome of the thermodynamic product, stability of the product. And likewise one can produce just similarly, just you increase the number of the carbon chain, and you will be ending up with this product. And also like this, that means what I meant to say, this same reaction can be extended to preparation of the higher ring systems. Let me give you one more example. That means still we are talking about the radical generation from the bromides, and in this case it is a heterocycle here. So, the starting molecule is in heterocycles with pyrimidine nucleus, that carbon pyrimid, and there is then you have an oxygen and phenyl ring, and you have a bromine ring here, the bromine atom here. Now, as usual, tertiary butyl tin hydride, you can say that is generated from the butyl chloride, etc., and the typical solvent is benzene or toluene, and if it is benzene, the temperature is 80 degrees centigrade. Okay. So, what does it tell you? In this case, a bromine sitting on the aromatic ring also can produce the phenyl radical. So, that is it, nothing else. So, previously it was sp3 carbon atom, now it is an sp2 carbon atom, that can be also generated by, and plenty of reactions have been studied under these conditions. Once the radical is formed, then you have to see and under okay, there are all of us by now know that there are all kinds of reactions. It can the radical generated can form a 6 member as well as a 5 member, and normally 5-XO is more favored. So, what you will get, there would be intramolecular reaction would be taking place. So, you will have rest remains as it is, and you will have a 5 membered ring, and these corresponding the benzene ring systems. This is a typical one. The yield is very good. So, sorry, it should be 5 membered. It should be right. So, it is 5 membered 1, 2, 3, 4, 5 membered systems. I will give you one more reaction. One more reaction very is quite similar, but they are strikingly useful. If you here is an example where you have side chain with X could be iodine or even selenium pH, that is phenyl selenyl, and this nitrogen contains a double bond and another double bond with NH and a C. Okay. The reaction condition all again kind of, that means AIBN. It could be tertiary butyl tin hydride, and this tertiary butyl tin hydride can also be substituted by any other kinds of hydride. Any idea? Anybody knows? What are the other possible hydrides? There are hydrides, right? Hydrides means normally we talk about metal hydrides. If we do not talk about the metal hydrides, then we go to talk about boron hydrides. Boron hydrides also are classified sometimes as the metal hydrides. What else? There is one more hydride, one more kind of hydrides. Right, silane hydrides. So, actually I did not get the name, but it appears to be, there is a name in my note, this TT something like that, TTM SS. I think some silane, I have no idea, but the silanes are plenty in literature, they are commonly used. So, essentially basically the radical set and this temperature radical conditions, then temperature is this. Now, let us say what do you expect? What do you expect? While iodine is there, hydride is there. So, a radical would be generated. That means the one that what one would expect, this radical would be generated. Now, you have this NH and OAC. So what next? 7 membered ring formation. So, there is 7 membered ring formation. That means sort of a Michael reactions. I mean, although you have amine would deliver the lone pair in the reverse directions, but this, so this is not a very good Michael acceptor, but yet the reaction would take place, and here you have this okay, actually in original compound you have an ester group here, ester group, and what you will find, a bicyclic compound, with a 7 membered ring, and then you have this NHAC, and here you have this ester group. So, what is the conclusion from this one? That means you do not have to have a very good, the 2 examples tell you that you do not have to have a very good Michael acceptors, but still the reaction can be done, and then again this NH is not not protected, as partially protected, that also would suffice to induce the cyclization. Okay. Let us look at one more very useful reagent. I do not know whether you know or not, samarium iodide. You have heard of it, right? What is the use? Actually, what is the use? Anybody knows? Any idea? Radical generation, that is okay. Carbonamine, carbon and radical. So, I mean anybody can say okay. What else? Or you can say metal transfer agent. Not really. That is the for yes, I will take it. Good. Yes. That is too general. You have to be a little more specific. What you said is correct. Carbon-carbon bond formation. That's like what he said also is correct. That it can be used for desulfonation. Yes, it has. some resembles with not McMurray coupling, or you can say pinnacle coupling. So, it could be a substitute for the pinnacle coupling. So, that means it forms the carbon radical from the ketones, that is important, not for the ester. Carbon radical, like say pinnacle rearrangement, pinnacle formation. What is the metal? Magnesium. Magnesium in inert solvent, not in protic solvents, etc. So, there are not many substitute though, there are not many substitute. What are the other substitute? Let us say if you do not have magnesium, what else would you use for pinnacle rearrangement? Sodium, I never heard. For pinnacle, for pinnacle. Maybe I have forgotten. It's too okay. I don't know. Anybody supports him? No. Any case, there are not many substitute though. But one person tried to develop a substitute for magnesium in pinnacle that was based on, at the moment I do not recall, it is low valent vanadium salts. S. Pedersen from California, he tried, and but this samarium is a very useful one. Samarium is useful one, but how useful I do not know, but today we will be seeing that it can produce the carbon radical. Carbon radicals from, that means oxycarbon radical, oxycarbon radical from ketone. That means if you start with a ketone and this oxygen up here, and then let us say you have an alpha beta unsaturated ester, you get an intermolecular reaction. Under the conditions, the condition is very simple: samarium iodide, then tertiary butyl alcohol, and room temperature. You do not have to heat and do anything, just room temperature. So, what do you expect? What I said, that it first forms a radical, that means anion here and a radical here, that is R1 and R2. Now, we have a substrate which is a Michael acceptor, and most often I said its carbon radicals are nucleophilic in nature. So, after the reaction is worked up, what you will find, if you write this ester in this fashion, okay, normally I write, okay, I think I should write this ester group here, then R4 and this is R3, that means it goes to the this one. So, that means alpha beta position. So, that means it is equivalent to what you can say R1, okay, R2, and here you have R3, then you have this R4, and you have ester here, and you have an oxygen minus. So, anion radical, and obviously, and all of us know, you have 5 membered, whenever you have a possibility of 5 membered 6 lactinations, that proceeds very smoothly, and so eventually what you get is, again it's of furanone now. So, eventually what you get is the, I mean furanone, you can call it as a lactone, and you can call it also you can call it as a heterocycle. So, you have all kinds of things. It is a nice reaction, intermolecular reactions. Now, I mean the same reaction, like let us say now we just change this, if you have a definite substrate up here, what you will have now, NH CBZ, carbonyl benzyl oxy, and this is R1. Then again you have a Michael acceptor, and what do you expect now? Just straight away write the product without looking at the reaction mechanism. Just then the methyl group up here, this is the methyl group, and this is NH and CBZ. Then that means you have a what you see here. So, why did I choose this example? Okay. This has also a why did I choose this example? Any idea? This reactions also is carried out with samarium iodide. The reagent condition is methanol, samarium iodide and 0 degree, that means that was previously at the room temperature, this is 0 degree. And what is remarkable about this reaction? Remarkable, it is remarkable in many respects. Number one, that you get 3 different chiral centers fixed. Under the influence of one chiral center, you can get the 3 different chiral centers. You are forming a new carbon-carbon bond. What else? What else? That is what is important in see in case of carbonyl compound having an alpha chiral center, many often you will see the racemization or the stereomutation takes place. So, but in under the radical reactions, elimination does not take place, racemization does not take place at the alpha positions. So, these are the advantages with samarium iodide or the radical kind of reactions. Let me give you one more. Many of you know the polyethers. Polyethers are very useful biological molecules. I will just give you only one example maybe, and that will tell you how useful is samarium iodide. Or rather, if you think about alternative methods, you will not find an alternative method for this. Here is a tetrahydro pyran case, oxygen up here, then you have ester, and I will just give there are plenty of examples in my note, but I will just give you one here, and once again samarium iodide, what else you require? Methanol, and the reaction methanol THF, and the reaction condition is room temperature. I think all of us should be able to write this structure, right? What is the structure? This that means okay. In this case, this here it was trans. So, that means this ring juncture stereochemistry remains unaltered, and mentally you have to work on that. Okay, the samarium iodide actually reacts with only ketone compounds. That means it will form an oxygen negative and carbon radical. So, an anion radical is produced. Once your anion radical is produced, either they undergo coupling, self coupling, or intermolecular cyclizations. That's it. That's it. That means this radical would attack the intermolecular version, and eventually what you will find? You will find a 7-membered ring, right? That means 1, 2, 3, 4, 5, 6, 7, 7, and this stereochemistry as usual, especially when you have the polyethers, you will find all these hydrogens across the heteroatoms are normally cis because of their anomeric effects. This hydrogen, and here you have, then the lactonization takes place because you have an alkoxy. This alkoxy expels the ethoxy groups, so you get the lactonization done. And so, what else? What is the other thing that you can think of? Again, there is no elimination taking place. See, when Michael addition takes place, had it been a carbon ion, you would have expelled this oxygen substituent. So, in that case, you would not have obtained this middle ring. So, that means what you can that means you can nicely construct the polyether, like if you begin with other ethers on the left hand side, etc., you can generate polyethers. Fine. So, this is basically a good example of the samarium iodide case. And now, we move on to just say again a different kind of the examples, that is it, and but the mode is very similar. I think this is what you have to see, that this is this methylene dioxide bridge here, methylene dioxide, this is oxygen, CH2 oxygen, and tertiary butyl tin hydride, TBH we write, AIBN, and then toluene. This is the commonly used sets of reagents and conditions, and then temperature 80 degree, though toluene it can go up to 110, and what is the product. So, now we have a sufficient of experience to predict the product. So, what could be the product? What could be the product? You start from the reagent. Whenever you have to predict a product, you start from the reagent. So, TBH is typically generates the radical either at the sp3 or sp2. So, it will this. Then what? Then immediately you should think of the intramolecular reaction. So, it can form a 3 member, right, but there is no, this double bond is not that electrophilic in nature. Okay. But instead you have a radical here, there is a possibility that it can undergo reactions with the heterocycles, that is it. Here it is a sort of a Minsky reaction, carbon radical, but Minsky reactions, if you recall, that involves normally the sp3 carbon atom, and eventually. So, this gives rise to a fused heterocyclic ring system, and you have all these that means. So, that is what you have to be little careful about, or you can, I mean, that these heterocyclic systems also could be an electron sink, means it can accept electron, and so there are other examples, maybe let me, I think I will skip some of the examples maybe, and there are most of the examples are typical examples of this tin hydride, etc. I think I will skip some of them, maybe I will give this one. This one is quite little interesting in the sense that you get 2 heterocycles if you have properly designed substrate. You have oxygen up here, again these beta oxy acrylates, and then you have a side chain with bromine, and you have one more unit of the beta oxy esters, then hydrogen, and you have 1 2. So, this 1 2. So, this is bromine, sorry. Okay. So, bromine. Now, I think again I think I will write this, just do, means on the whatever written on the top is this. So, what is the product? Any idea? What is the product? I mean, this is I mean both all, I mean all the side chains are, this is same as this one, this is bicyclic ether, that means 6 member bicyclic ether. Okay. So, that means at least we know that sp, that means radical would be forming an intramolecular reaction. That is a typical, actually there are plenty of reactions of this kind, and only thing that you have to be now little careful is that the reaction gives a. So, what is the conclusion? So, you have a competition now, you have competition versus 5 and 6, and often 5 is more facile, Okay. So, I think we have talked about enough of this thing. I will give you one more example where very similar, that radical being generated from yes, let us say, I think I have many examples. This is a case many of you would not know, because this is a specialized case. Here you have an heterocycle, and then you have an ester group here, and then it is now CH2 and bromine, and the reaction set again TBH, typical this AIBN, and the solvent and then heat. So, what do you expect? If you know that Dowd ring expansion, then Dowd ring expansions. Paul Dowd, he has unfortunately died at early age. He was in Pittsburgh, and he had a nice way of ring expansion. If you have a keto compound, normally cyclohexanone, how do you go to the cycloheptanone? In the honors level, most of you write diazomethane, right? Diazomethane, but those reactions are very lousy reactions actually, the low yielding reactions, etc. But he developed a nice protocol for ring expansions. This is something this like. So, what you see here, it first if you stepwise proceed, then what you will find, the reactions are pretty easy to tackle. So, you have now radical here. So, what next? What next? What next? Intramolecular reactions. How is that? Intramolecular reactions. Now, see, this is a combination of very interesting. This is not a pyridine though, the middle ring is not a pyridine ring, but it has some advantage. You get a radical alpha to the nitrogen. What does it mean? You have an extra stability, although deorbitation is taking place, but the radical that is being generated, it has some it has gained some due to this lone pair effect. And so, you will have the ester group here, and you have a triple bond. What next? If it goes back, then you get the starting material or the starting material. So, rearomatization and the ring expansion takes place. That means, the middle rings now becomes a 7-membered ring. So, that means, I mean, you can logically approach and eventually you get to the right answer. And I have many more examples. I will skip them. I think very quickly I will go to the last example. In the last year, we talked about a reaction, right? We talked about the radical reactions of cyclopropyl methyl radical in the context of establishing the radical reactions. What is this? It is a radical probe. Anybody knows what is the meaning of radical probe? I mean, if you want to distinguish the reactions, whether it is a carbonium reactions, radical reaction, or carbon ion reactions, one of these way is to use this sort of radical. It opens, then the reaction must be considered a radical reactions. If the cyclopropane ring is open, that means the adjacent atom was a radical. Okay. Now, if you substitute this, with a let us say metal, that means oxygen up here and it is a cyclopropane, right. Now, if you coordinate with a metal and metal has a let us say additional electron pair, then there is a chance that it would open up. And it will give rise to something like this. So, what is it? So, that means you have to have a metal which is a reducing agent. What do you get out of this, and how do you call it? This is a radical having an oxygen minus, you can say. If you recall, the samarium iodide produced a radical onto the carbon having the oxygen. Now, it is at the beta position, and this sort of reaction is done in cultivation of science almost regularly by Subhas Roy, and it was invented by one Indian scientist, Rajan Babu at Ohio State. Have you heard of him? Okay, Rajan Babu and some other person when he was in an industry, not in Ohio State. And the reaction is just, I will give you just only one example. This is a nice reaction though, nice reaction. if you let us say begin with an epoxide. So, that means what is the requirement? You have to have epoxide and let us say R oxygen propyl group, oxygen and this. Okay. So, and the metal here Cp2 titanium chloride, that is it. So, that means reducing metal salt, reducing metal salt. Okay. So, it gives that means now you have two things here. You have a radical opening on this side, you have a radical opening on this side. All of us know radical, like carbonium ion, secondary radical is more stable. So, the radical that would be generated is then is oxygen minus up here and the radical up here, and he has published plenty of papers in this thing. Since we do not have time, we will this. Okay. And so, what else? That is it. That means what we will get 1, 2, 3, 4, 5. So, we will have again a furan ring R, and then this is now double bond, and you have OH group here. So, you have an OH functionalized furan, and all the carbons are almost like functionalized. This is having oxygen, this is having oxygen, this is having sp2 carbon, and this is also CH2 having, it is a functional group, and this compound eventually converted into a natural products called it's natural products something like methylylactone or something, and it's a natural products with this, and it has this R group up here. So, in multi steps they have been able to produce this. So, this is another unique way of producing a radical. Okay. And so, what else? I think we did not give you examples. The time is now okay, up. Then one more example I think you have to take note of, that is phenyl iodinium diacetate. So, phenyl iodinium diacetate is also becoming a very popular radical generator. Okay. And often it is used to produce radical from the benzylic positions.